Hi, so my name is Bill Buchanan and I lead a podcast on the world leaders in cryptography. And today I have a true world leader, Craig Costello. Hi, Craig.
Hi, Bill. Thanks for having me. Nice to meet you.
Yeah. Where in the world are you just now?
I'm in Australia on the East Coast in Brisbane. I moved back here about a year ago. I'm in the middle of the summer at the moment. It's 5 past 10 at night, but it's still pretty hot. So I've still got the air
Oh,
conditioning going, and yeah,
okay. You'll be glad to know that it's about 5 centigrade in Edinburgh today, but it's sunny. It's winter time here. So we're coming out of winter. You're probably coming out of summer, but your summers are obviously different to the ones that we have in the UK.
yeah. Our summers tend to go for most of the year. I think by relatively speaking, it's feels like summer at least for 9 months, and our winter's more like a very mild spring.
And you were based around Redmond?
I've been in at Microsoft Research there in Seattle, in Redmond
Yeah,
for almost 15 years.
yeah.
Yeah, since about 2012 until a year ago. A year and 2 days ago, I started my new position back in academia. But for the decade plus prior to that, I was in at Microsoft in Redmond there.
Yeah. And I assumed the weather in Seattle was a bit more like UK weather rather than Australian weather.
Yeah. It was Seattle. It lived up to the hype of being rainy most of the year. So took some adjusting for me to get used to coming from this climate to that climate. And I ended up. I think now that I always felt like I missed the summer and missed the heat, but now that I'm back, I kind of miss the seasons too. That we don't really
Uh,
have the seasons here in in
yeah,
Australia. It's more like the endless summer. But
yeah.
yeah, when
Oh,
I see people, rugging up for the fall and then really bunkering in for the winter and stuff, it's there's a bit of nostalgia there, but I'm kind of also happy to be raising my kids in a climate where I don't have to get them dressed in 3 layers to go outside and start crying because it's too cold. So happy to be back home.
good. Okay, so home is that you're an Australian. Where were you
Yeah.
born?
So I was born in Canberra, which is Australia's
Mhm,
capital city, but
mhm,
was basically grew up here in sunny Queensland since I
mhm.
was 3 years old. So did all of my undergrad and PhD studies here in Brisbane, and then kind of went abroad since I finished my PhD. For most of my adult life, I've been abroad, but
Yeah,
once we started having kids, and I kind of wanted to move back and be close to family and
yeah.
close to what I knew, what I grew up in, and those sorts of things. So yeah,
I
made the
suppose
decision to come back.
yeah, it's a rites of passage for many Australian people to leave and
Yeah,
come
and then come
back
back.
again,
Yeah,
see
it
the
feels that way.
world, and
Yeah,
then come back to your home
yeah,
again. So, so Craig is a professor of computer science at Queensland University of Technology, or QUT, and who has a special focus on post-quantum cryptography and zero knowledge proof and many other areas around that. He was previously a principal researcher at Microsoft Research at Redmond. Craig also did his PhD at QUT from 2008 to 2012 and received a Fulbright Scholarship with UC Irvine from 2010 to 2011. In 2015, Craig published details of the FourQ elliptic curve, which we'll look at a little bit later, and which is one of the fastest elliptic curves around. So, what's your current role and what does a typical day involve for you?
yeah. So I think my current role, broadly speaking, is very typical academia. So it's supervising, teaching, trying to get some time to do research, and also since I've kind of come back, having been out of academia since my PhD, a lot of grant writing too, a lot of trying to claw for some money and for some funding. So a typical kind of a typical kind of day is all of those things, and it's been a bit of a rude shock to come back to academia, having had a very kind of cushy industry research position where basically almost all of the time, except for the odd meeting, you're doing research and looking into whatever you want or whatever's exciting at the time. Now having to juggle all of those other things, I'm very, very humbled by having to manage my time and still trying to think about research and read the papers that are landing on the archive and all those sorts of things while doing all of that other stuff. It's made me appreciate all of those of you that have been in academia and managing all of those things for a long time. And yeah.
I think it's a bit like being self-employed. Basically,
Yeah.
you're giving a whole lot of things that you need to do, right? Write papers, research grants, and teach students and so on. And then there should be some flexibility. So the advantage is that it's fairly flexible in how you implement, and there's a lot of trust in the system. But you're right, it can be a bit scary for someone coming from industry back into academia, especially getting grants is quite difficult. I don't know
Yeah.
what it's like Australia, but in the UK, it's getting tough. In the EU, Horizon projects are getting tougher. And obviously, you need PhD students and you need researchers and you need to build a team. So can be quite difficult to come in. And then obviously, you've got established researchers who have built their own team and have their own money and so on. So it's a difficult thing. And obviously, Microsoft had big pockets of money
Yeah.
that they
Yeah.
could actually spend. But they'll be looking for a bottom line, I would think, for everything that you did. They would be looking for something that had commercial benefits overall. So how did you get into cryptography? What was your school days like? How did that progress happen from this kid at school to someone who's a leading researcher in cryptography?
Yeah, in my case, it was, I kind of always loved mathematics, all the way through school from grade one onwards. It was the thing that I kind of, fell in love with at an early age. And the one subject I felt really comfortable in. And so often, I think thinking back to most of my school years, I was finding excuses to do little maths problems in all of the other subjects, and so I knew that I wanted to go on and just continue to study maths at university, and so I did that, and I think where I went at QUT here, there's a big focus on a lot of the applied mathematical sciences. So there's a lot of statistics and calculus and analysis and things like that. And once I had a taste of the broad field, I decided that those sorts of directions weren't for me. I was much more keen on I guess I would very biasly call it the more elegant and beautiful mathematics, the kind of number theory and the geometry and things like that.
Okay.
And so then once I realized that that was the sort of things I like to think about, and looking for patterns in numbers and talking about primes and all those sorts of things. Yeah, I guess if you're going to be a pure number theorist, you're either going to be, someone who's a Fields medalist worthy, and I didn't think that was ever going to be me, or you're going to be someone that looks to apply it in the real world. And the one place that it's really, really applicable, fortunately, is cryptography. And so I was lucky to be exposed to cryptography very early on in my undergrad, and then took the more advanced courses and stuff like that. By the time I finished my degree, I'd had a really good taste of it. But then in the last year of my undergrad, 2007, there was a conference midway through the year that was organised by some cryptographers at the university, and I was just a fly on the wall at that conference. The conference was on pairing-based cryptography, and at that time I didn't know any of the names that were speaking, but I sat in on a lot of the lectures, and Mike Scott was giving a talk, and a lot of
Mike
other
Scott
leading
from
names.
BLS,
Yeah,
Irish Irish cryptographer, I think.
absolutely,
Is that
yeah.
is that yeah?
One of my very early and still academic heroes.
Yeah.
Yeah,
I
yeah.
agree.
And so he was
I've
kind of,
spoken to
I
him.
guess,
He's yeah,
oh, you have? Okay,
yeah.
great, yeah. No, and so I saw his talk, and I saw a bunch of other world famous pairing based cryptographers speaking there. Um, and then I started to look at some of the papers on pairings because I thought that that's mathematical. There's some computation. There's a little bit of number theory. And then I remember reading a few of Stephen Galbraith's papers as an undergrad, and I thought this is what I'm keen to do next. So I was very lucky to have a project in pairings, kind of sitting waiting at the university for a keen student to do as a PhD, and that's where so I took that jump into pairing based cryptography for my PhD, and I guess the rest is history.
Yeah, I mean, you've obviously got people like Jan Kamenisch who did a lot of amazing work at IBM, and we'll come back on to pairing-based cryptography because it's so powerful. So I assume that you're teaching just now. I don't know what types of classes you're actually teaching, but what's your favorite topics that you like to teach?
Yeah, well, definitely all. It's kind of remained all of those things that interested me to begin with. So cryptography. I love to teach cryptography. I love to teach the kind of introduction to cryptography because I guess there's a bit of nostalgia from having been really excited when I saw it for the first time. When I saw kind of public key cryptography and didn't really understand that it could even be possible until, and I think even now teaching it, I'm still blown away by Diffie-Hellman. I'm still
Yeah,
it's still magic to me. It's still my favorite paper.
yeah,
And so I love kind of trying to share that excitement with undergrads, and 9 out of 10 of them it might miss, but when you see it hit and you see someone get excited too, that's what I'm enjoying already about teaching, and certainly the kind of the foundational mathematics behind public key cryptography. So the elliptic curve group law, that's another thing that's like, I'm very accustomed with, but it still surprises me that it works and that it's, all of the properties that we take for granted, when you're teaching it again, you can still be surprised with the elementary stuff. So I
yeah,
love to teach those sorts of introductory courses, and then getting into the more advanced cryptography stuff as well is fun. Um,
yeah. Yeah.
yeah,
When I spoke with Neil Kobolitz and Victor S. Miller, they actually didn't know at the time what they actually had, how amazing it would be. It took many years for elliptic curve cryptography. And if you look at the handbook of cryptography, which is where I learned a lot of the underlying theory, it doesn't even cover elliptic curves. It's one thing they missed out
yeah,
overall. And I think elliptic curves are just so beautiful. And hopefully there'll be a place for them in a post-quantum world. But we can talk
yeah,
about that
absolutely.
too.
Yeah, yeah. I'm
So,
holding on to that same hope. But yeah,
yeah.
I saw Neil and Victor's. They gave talks last year because it was the
Mhm.
40th anniversary of elliptic
Yeah.
curve cryptography.
Yeah.
So 40 years since their two papers landed. And they kind of gave talks at the annual
Mhm.
like virtual talks at the annual ECC conference. Um,
Yeah.
and that was more kind of historical, kind of biographical talks of how they came up with those papers, and it was really fun to try to put yourself in their shoes back in those days, and to think to think of how cool it would have been. And it's also cool to see that they had no idea what they were starting,
Yeah. Yeah.
and how many of us would become obsessed with it down the track.
Yeah. I've just been a co-author on an elliptic curve paper, and it's like an analog elliptic curve paper. And it's quite difficult to find integer points on a true elliptic curve. It's really quite challenging to find all the integer values that x and y would be that an
Ah,
elliptic
right.
curve goes
When
on. But it's
if you're
amazing when you
considering it over the
bring
rationals kind of thing,
that's right. If you
or over
don't
the
have
integers.
a mod p, obviously mod p brings it in so that the order of the curve, the number of points, actually becomes quite near the size of
Mm,
of p. But when you're
yeah,
dealing with an analog curve, it's actually quite difficult to find all of the possible points on the curve that are actual integers.
yeah.
And
I think
it was,
this is one of there's the problem of determining the rank of an elliptic curve.
yeah,
So when you're considering them over the rationals, it's how many kind of unique infinite subgroups are there?
Yeah.
This is the problem of determining the rank, and it's still very open. There's one of the millennium problems is related to this, and yeah, there's a lot of open problems in that field. But I think the kind of away from cryptography, a lot of the fun that a lot of the interest that mathematicians have with elliptic curves is they're kind of the simplest geometric object that if we talk about curves of the simplest geometric object, things in x and y,
Mm.
and you can talk about linear equations like y equals mx plus c, which is a line, and that doesn't really, there's nothing too interesting geometrically about that. And then we can talk about degree 2 equations, and I think we know everything there is to know about finding all of the solutions, integer, or
Yeah.
rational or otherwise, of those. And then as soon as you go to degree 3, you get an elliptic curve, and then what we know about them, we know a lot, but what we don't know is probably much bigger. So I think that's part of the obsession from mathematicians, is that these things, that there's already very, very difficult problems even at degree 3.
Yeah. And it's probably got another decade at least of good implementation. Trillions of connections every day are still
Mm.
using ECDH and X25519. They're using ECDSA, EDDSA, and blockchain, and so on, and ED25519. And we're still using RSA too, but elliptic curves have come along and they've been amazing. So just to outline to the readers, if you have something like the Bitcoin curve, which is SEPT256K1, not R1,
Mm-hmm. Mm-hmm.
you have y squared is equal to x cubed plus 7 mod of a prime number in there. And then we end up with a whole lot of points. It's not quite as beautiful as the elliptic curve, the analog one, but we end up with a whole lot of points. And the difficulty in elliptic curve is that if I take one point and I add another point, it gives me another point somewhere, and it's really difficult computationally to find the 2 points that created that point. Is that a good explanation?
Yeah, it's a great explanation. I think so yeah, what you're describing is the elliptic curve discrete log problem. And so I think that was the whole, back when Diffie and Hellman published their paper to show what you could do with the integer discrete log problem, modulo a prime. Then it was Miller and Koblitz that came along and said, well, if all you need is a group, then here's a group that looks good. And I think and it says it in their paper. In Miller's paper, there's a sentence right at the end that says it appears that this will be immune to index calculus, which was the whole kind of, I guess, one of the motivating factors was that if you do integer discrete log problems, you can do index calculus by kind of lifting away from the modulus and just treating them as integers that have small factors, and you can come up with factor bases and do index calculus. But on elliptic curves, there's no kind of analog of a factor base or of smallness or anything like that. And that intuition that Miller and Koblitz put forward 40 years ago, what's amazing is that it's 40 years later, it's still very true. This elliptic curve discrete log problem that you just explained is, I think, from what I can, don't quote me on this, but I'm pretty sure if we're talking classically, it's the only concrete example of a group we know that's as hard as the generic discrete log problem. So, which is to say that the best algorithm for the elliptic curve discrete log problem is Pollard Row or, baby step, giant step, these kind of square root algorithms
Yeah.
that can work on any group.
Yeah.
The amazing thing about the elliptic curve discrete log problem, if we're ignoring the quantum threat, is that with all of the structure and beauty that elliptic curves offer, there has been no better algorithm for a well-constructed instance of the problem. There's no better algorithm than generic, which is amazing.
Yeah, because we went from John Napier's logarithms g to the power of a mod p. That's obviously quite a computationally intensive processing towards more a multiplicative a times the base point. So we have ag, and then Peter Montgomery came along and said, look, it's quite easy for us to
Yeah,
do this computation of a times g, the base point. And the great thing is, just as you're saying, if I have ag and I know g, the base point on the curve, I can't compute a. How magical is that?
yeah, it is. It's still magical, and it's a part of me. It's the quantum threat that I'm sure we're going to talk about is has been fun to shake up the field, but part of me is a little bummed that that we're going to be saying goodbye to the elliptic curve discrete log problem at some point. That there'll be at some point in the future, there's going to be the last pure ECDH or ECDSA or
Yeah.
EDDSA or whatever. There'll be the last one, the last standalone communication that's secured with that problem. That's that'll be the end of an era, but it's definitely been fun while it lasted.
Yeah, but we've got hybrid. I think we're looking at hybrid X 25519 along with MLChem and so on. So I think certainly to make sure that the TLS stack stays roughly the same, we'll have to start to look at. I think there's a method called X-Wing, which is quite
Yep,
interesting, which stores both the X25519 public and also along with the ML Chem one.
yep,
So I think we'll see the rise because it's a big jump to just change everything over and we've got to look at the digital certificates and things like that. They're going to get a lot bigger and they're going to have
yep,
more than one key. But maybe we can chat a bit more about that. But you're right. I mean, the mathematics and the beauty, once you get elliptic curves, then it's just wonderful. So the biggest problem is finding the square roots equivalent, uh, and we end up with 2 points typically. We end up with just like a square root gives you a plus and a minus. We end up with an x, and we end up with two y points, typically an odd and
yep,
an even. And then we have this thing with the compressed points or uncompressed. 0, 4 is great in elliptic curves because 0, 4 gives you the x and the y. And then we've got 0, 2 or 0, 3 gives you just the x coordinate. And then whether the y coordinate is 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 odd or even. So it's good. It's good. I mean, I like it because you can just look at things and they're just so small, the key
yep.
sizes and so on. RSA is obviously much bigger. So, what's your current research focus at the university?
Yeah, so at the moment I'm still I would say my main focus is still post quantum. For a while it was my only focus when I was working, I guess, almost exclusively on isogeny based cryptography.
Mhm.
And we might talk about what happened there, but yeah,
Yeah.
I was working on
Yeah.
a submission for the post quantum
Mhm.
standardization effort. And when when things went a bit pear shaped there, um, there was also some management changes internally at Microsoft, and we were encouraged to look at something else to move it. I guess once the psych was broken, management were encouraging us not to do. You don't have any more NIST submissions alive, so go and work on something
Mhm.
else. And even though as a researcher that kind of makes you uncomfortable being told what to do, which is another nice reason to be in academia. I also understood, they're looking at us wanting to produce things that are going to have impact and be meaningful. So for me personally, I was surveying, looking around the area, going where else are elliptic curves being used and active, and at the time so I got back into pairing based cryptography. That I'd put that on ice basically since my PhD. I hadn't done much at all in terms of in pairing based crypto. But since I'd left that subfield of cryptography, there'd been a big explosion into pairing based zero knowledge proofs. So I was kind of keeping a loose eye on the literature from afar and seeing a lot of activity in the space and thinking, oh, this is all very weird stuff that they're up to. I didn't really understand what was going on, but then taking a break from isogenies for a while made me get very interested in that. And so now I'm deeply interested in the problem of, in some kind of esoteric problems that lie underneath pairing-based zero-knowledge proofs. So I'm working on the kind of constructive curve implementation aspects that sit below these, Groth 16 and those sorts of pairing-based zero-knowledge proofs. Trying to find better constructions there. And there's these kind of little funny problems that come up with constructing pairing-friendly curves. It was already difficult enough to construct one pairing-friendly curve, but in the zero-knowledge space, you often need more than one, and they need to be connected in a way that feels unnatural and adds more constraints than you already had. And so for me, that's been a lot of fun to try to see what's possible there, and I'm very involved in looking at that. Nothing exciting has come up yet, but I'm hoping it will. Sorry, my dog's just come to to say hello. And then the other thing I'm trying to get into, I guess I'm kind of starting from day one of a student. What would be a student, day one of a PhD, I feel like, but I'm getting into quantum algorithms slowly because I want to see if I can think about quantum algorithms for cryptanalysis. So I'm starting to go and look at old lecture notes and start from scratch in that regard and teach myself quantum algorithms with the hope of kind of maybe building some capacity here with a team that might be able to do quantum cryptanalysis, because I think globally that's something that's probably very there's not enough people that know quantum algorithms and know cryptography. There's already an incentive problem globally with working on cryptanalysis, which is to say, very good people can work on it for a long time and come up with nothing, and therefore not be publishing anything, which makes incentivizing cryptanalysis hard unless you're very good at it. And then so already it's, cryptanalysis. I think a lot of people it wouldn't be controversial to say there's not enough of it happening. And then if you add the quantum on top of that, I think that's something that's really needed. So now that I've kind of got what I hope is my long-term position here and maybe a little more job security, I'm hoping I can kind of take that time to invest into some quantum algorithms and see if I can get up to scratch with what's out there, and maybe try to do some cryptanalysis myself.
Yeah, I agree. I met with Jens Groth, and it's really interesting that paper in 2016 really just changed so much. And he thought he had the shortest zero knowledge proof value, but
Mm-hmm.
he said that someone else created an even smaller commitment for that. But his paper is wonderful overall, and it's one of these papers that you could pick up and you go, is there anything special here?
Right.
And it's obviously the industry has picked it up greatly and ran with it overall.
Yeah.
And I think you're right about the cryptanalysis, because obviously with qubits and the opportunity to do things in parallel. So I
Mm.
think we have obviously Shor's algorithm, which will break the discrete log, but Grover's algorithm actually starts to break symmetric key and hashing methods up to about 128. There's still some debate about it, but and there are things like you can do a perfect one-time signature in a quantum computer and never have the private key released that you can't do in a classical world. So things like quantum money might
Hmm.
actually be
Hmm.
possible, where you can create uh, a coin in a quantum
Yeah.
computer.
Yeah.
But you couldn't really do that in a classical, because someone can always take a copy of the private key overall. So I think that's such an interesting area. It is like quantum machine learning and so on really would
Right.
open
Right.
up. But I think the competition has got to be big, and obviously the hardware has got to be there. So hopefully academia will have a bit more hardware quite soon. So
Yeah. That'd be nice.
You came up with the 4Q curve while you were in Microsoft. What was the motivation in designing that curve, and what's its core advantages?
Yeah, the the motivation was, if I'm honest, the motivation, it kind of, this was I've had a couple of papers that I guess that was coming off the back of my first kind of experience looking at or participating in a standardization effort back when the IETF were calling for new elliptic curves. I think this was kind of off the back of the Snowden leaks and maybe some distrust in the NIST curves, or some potential distrust in the NIST curves. The IETF opened up the door for new elliptic curves to be there, and we now know that Bernstein's 25519 curve and Hamburg's Goldilocks curves were chosen as a result of that effort. And it was very eye-opening for me to be involved, like participating in that. Myself and a team of researchers at Microsoft, we kind of came up with our own proposal of what we thought was a good idea. And there was a lot of heated discussion on the mailing lists and things like that about whose curve's better, whose curve's faster, and this and that. And that curve, the 4Q construction, kind of came off the back of that effort after we got beaten pretty badly. Like we didn't, our curves didn't get standardized, which is totally fine. But we also, I think it kind of inspired that work, in that a lot of the discussion, we would put forward, or we were putting forward an idea of saying, we could use this set of curves, and then, some people were saying, oh, you obviously don't care about speed if you're willing to pay that 10% additional overhead just for this, whatever. And so I think there was a bit of I guess a bit of academic vendetta to say, oh, if you think we don't care about speed, then I'll show you speed. And so myself and Patrick, who co-authored the paper, the idea in that paper was to basically, let's just throw all the tricks that we can put into one. Let's find a curve that's as fast as we can possibly go, where we're not violating the kind of high level security picture of, we still want the best attack to be generic Pollard row, but other than that, all we're free to use all of the optimizations we can, because in the discussion of what was allowed and what wasn't allowed, and what's a good security performance trade-off and those sorts of things, it was very unclear and ad hoc. And so certain things were, you wouldn't want a low embedding degree, for example, so that they could use a pairing to move the discrete log to a finite field. Everyone agrees that that's a really good idea. But then there's a lot of other kind of little things, should it be prime order? Should it not be prime order? Well, prime order is a bit slower, but then you don't have small subgroup attacks. And, there's a lot of trade-offs there that were where the trade-off kind of we thought warranted discussion. And so on the back of getting beaten in that standardization competition, Patrick and I just thought, let's just crank the speed up to 11 and see how many tricks we can combine into one curve. And so the advantage of the main advantage of 4Q is the speed. I guess it's, it was at the time we were, and I guess on modern implementations would still find a 2x or larger speed up over 25519, and I think it was a 4x speed up over curve 250 NIST 256. But because we were combining, endomorphisms with a very, very cherry-picked underlying finite field, complete Edwards fast addition formulas and doubling formulas on the elliptic curve. Basically, all of the kind of best high-level tricks were combined into one implementation. The other advantage that is, I guess we didn't really state in the paper, but it's something I've thought about since. the curves that are standardized, whether you're talking the NIST curves or 25519 or Hamburg's curve, that there was this argument that the NIST curves could have been constructed in a way that someone knew a vulnerability in them, but they've tried to convince us that it's randomly generated or random among the set of all curves over a given field, which was, I guess, the initial proposal. And then this notion of having nothing up your sleeve and basically once you define a finite field that's efficient to work over, there should be a process that spits out one curve. This notion of rigidity, I think it was dubbed back in the day. Basically, you're not able to search over a big class of curves to find your curve, because if you were being malicious and putting a backdoor in, that might allow you to do that. So the curve 25519 and Hamburg's Goldilocks curve, they make very good arguments as to, this is the one curve over that field, or it's the first curve following this process that is output over that field. The thing I like about FourQ in comparison is, like, those curves, I could argue, or one could argue, that there's not infinite, but exponentially many curves that are just as fast over those fields. There's an exponential number of curve constants that give you the same group order and the same high level security picture, and it would be just as fast, maybe plus or minus 1% performance difference, depending on the implementation. With the case of FourQ, that kind of all goes out the door, because it's kind of a unicorn that's sitting there on its own. There is only, as far as I know, one curve that has all the endomorphisms that you would want or could have without violating that high level security picture of Pollard Row being the best attack. So you've got two endomorphisms that you can use to speed up the scalar multiplication, and the chances of having that over a specific prime field, a specific characteristic field, it was kind of, I guess, folklore that you wouldn't be able to find a secure curve with both endomorphisms over a field that you choose in advance. So we chose the field the prime P is 2 to the 127 minus 1, which is a Mersenne prime. It's kind of the only Mersenne prime within those ranges. Which is very, very fast in software, hardware, whatever you like. And so we chose to work over the quadratic extension of that field because that gives you the Frobenius endomorphism. And so the field there's no arguments that that's the fastest field to work over. Now, you can't go any bigger than quadratic extension fields, because then index calculus becomes a problem. So if you want Pollard Row to be the best attack, you either have to work over a prime field or a quadratic field. And that, as far as fields go that are the requisite size, that's the only one, or the fastest one. There's no competition there. But the chances of there being a curve that has both endomorphisms and miraculously has a group order that's secure enough it was thought to be kind of very, very unlikely. There's no point searching, because there's only a handful of curves over any given field that have both endomorphisms, and the chances that one of those handful of curves has a strong group order is very small, because you take a random group order of that size, chances are that it's going to factor into prime factors that aren't where there's not a small cofactor and then a big prime. And that unicorn we found, when we were searching we thought, oh, what the heck? Let's just double check that there's not a secure curve with both endomorphisms over that field. And it turns out there was one that was just sitting pretty. From the handful that we could check, I think there's like at most 20 or 30 that we could check, and if you choose them over any other field, you can see that all the group orders are bad. You can't do secure discrete logs base cryptography there. But in this case, we hit one, and so the moment that we saw the group order come out to be, small cofactor, big prime subgroup that we could work in, the paper wrote itself, I guess. We were very lucky that the group order had a cofactor of 8, which allowed us to write it in twisted Edwards form. So we had the fast field, the fastest curve arithmetic, and all the endomorphisms, and it was like, okay, this is all the best optimizations into one. And there is only one curve. So the argument I have in hindsight is, if speed is the governing factor that's going to choose, the next generations of curves, then here's one that's chosen for us. It's kind of like the curve gods gave that curve to us, sitting on its own.
Yeah, because in hardware, every tick of the clock consumes energy, consumes the battery a little bit more, and I think most people don't take that into account, that actually the faster you can go, the less energy you're likely to consume overall. So obviously we're now seeing learning with errors used fairly extensively, or lattice-based cryptography. Could you explain us in a simple way how learning with errors works with post-quantum key encapsulation?
Yeah, so the way I like to describe it is to start with linear algebra. And so if you have a matrix and a vector, so a matrix vector product, we can start with a toy example of a 3x3 matrix and a 3x1 vector, and you do that matrix vector multiplication, you get a 3x1 vector as the answer. And we all learn in kind of linear algebra 101 that a matrix times a vector gives a vector, and if you want to, if you've got a matrix and an unknown vector, and you've got the solution over here, you can compute the inverse of this matrix and multiply it on the other side, and come and get the unknown vector that way. So if you start with that kind of basis of linear algebra, the way that learning with errors works. So first of all, you can obviously do linear algebra modulo, modulo primes or composites, and everything still works just fine. I guess as long as you can compute modular inverses then of the numbers, then you can compute the inverse of a matrix. So if we're talking about learning with errors, the minute you take a matrix, multiply it by a vector, you've got the solution over here. If you go and perturb elements of that solution vector, so you go and you might add one to this top one and subtract one from here, and then maybe you leave the third one. All of a sudden, Gaussian elimination doesn't work anymore, or inverting the matrix and multiplying it will give you something bogus as the solution. So at a very high level, learning with errors is kind of like linear algebra just with some noise, with some errors applied to it. There's a lot of caveats I'm sweeping under the rug, and probably many that I'm not qualified to talk about. But roughly speaking, it's just linear algebra, just matrix vector multiplications, but adding error. As soon as you add error to that solution over the other side, all bets are off in terms of, as far as we know, it's very, very difficult to go and find what that vector is when you multiply. One of the caveats I should say is, if we're talking about a square matrix, then the thing that the vector that it multiplies at has to be small elements for that to be at least a difficult distinguishing problem. That's just a technical caveat that I'll throw in there. But in general, if you have a linear equation like that, an equation that's from linear algebra, you can solve it. But the minute you start adding small errors to the result vector, then it's very, very difficult to find out what that, without knowing what those errors are, what the perturbations in the right hand side vector are. It's very difficult to know what the what was that unknown vector that you multiplied by. So the way that is turned into a key exchange or key encapsulation is so you and I, we're not going to work with the 3x3 matrix anymore. That'll be too easy to kind of brute force. We're going to up the dimensions, but all the math stays the same. So maybe you and I are going to work on a 1,000 by 1,000 matrix that you, me, and everyone else in the world, it's a public parameter, just like a generator of a group is in a discrete log crypto system. So we all might use the same matrix, a randomly generated matrix modulo a prime, let's say. And what I'm going to do is choose a small secret, a vector of elements that are small, very maybe close enough to 0 modulo that prime, plus or minus, let's say 10. And then I'm going to do that matrix vector product, and I'm going to also add some error as well. So there's going to be an additional error vector that's added there as well. So I'm going to do this matrix A times my secret S plus my error E, and I'm going to send that instance of the LWE problem to you. So you've got AS plus E. We'll call that B. So I send you B, just a vector. On your side, you're going to have a different secret and a different error, so S prime and E prime, let's say, and you're going to use the same matrix to do A times S prime plus E prime, and you're going to send me B prime. So we're both sending each other kind of noisy matrix vector products. When I get your B prime, I'm going to take my secret S and transpose it and multiply it by your B prime. You're going to take your secret S prime and multiply it by my and transpose it, multiply it by my B. And it turns out both of us have got something that's very close to S times A, or S transpose times A times your S prime. And you've got S prime transpose times A times S, which turns out to be the same thing. But we've both got something very close to that number with our own errors. So you and I don't have the same number, but we've got something that's very close to each other. And so at a high level, we've got different numbers, but they're very close modulo some large prime, let's say. And then the way we deal with that is we turn it, there's no way for us to do that exchange and land with the same number, which is the whole goal of key exchange. We want to arrive on a shared secret. So what we have to do when we turn it into a chem is whoever goes first. So let's say I was the one who went first. I'm going to give you a hint because I'm going to have already computed my based on your public key. I'm going to have computed my my share of the secret, and I'm going to do some sort of rounding, and then I'm going to send you a hint to tell you kind of how I rounded mine. And what that hint does is it tells you how you should round yours as well. So I'm going to send you a hint that says, okay, I got this noisy product. You're going to have a noisy product. I'm going to round this way, so you round that way. And that basically kind of gets rid of the error that's left. Because my error, I think, was S times E prime, and your error was S prime times E. I'm getting into the weeds here, I know, but we've both got slightly different errors. But as long as I kind of tell you how I rounded on my side, then that allows you to round to the same thing on your side. So what happens then is we kind of lose a bit of symmetry in terms of kind of classic Diffie-Hellman key exchange, where you can send me something, and I can send you something, and in theory they can cross on the wire. Neither of us has to go first. In this LWE land, because I need to send you that hint before you can reconcile your errors on your side, I have to go first. So I have to kind of encapsulate the key, if you like, and send it to you. So we kind of lose that nice symmetry that we had in pure discrete log-based Diffie-Hellman. And that's why these post-quantum lattice-based and code-based key exchange mechanisms, that's why they're phrased as chems, because this symmetry is lost with the noise. We need a way to kind of, one party always has to tell the other party, this is how we're going to round away from the noise. Otherwise, we're going to end up with different numbers. But otherwise, from a kind of high level, it's basically the same thing. In terms of what happens in practice, someone always has to go first anyway. And so, yeah, that's how these LWE schemes work at a very high hand wavy level.
Yeah, that's excellent. And obviously with Chem, we can also do public key encryption in the same sort of way, but it needs to be a small thing that we encrypt, and that can be a key. So I think that's obviously the focus on hybrid cryptography, that we're using the chem to encrypt, just like we did with RSA with the
Yeah,
public key of the other side. We encrypt uh, uh, the key, the secret key that we want to use and send it
yeah,
over. So people should remember that ML Chem is both a key exchange encapsulation method, but it can also be used for encryption of a
yeah,
small secret, and that's likely to be the way that we'll use our hybrid encryption, just like we do with X25519 to be able to exchange a key that could be used for symmetric, like PGP, GPG, and Box and things like that. So
yeah.
I know that you worked on Frodo Chem in the past, and it just didn't quite get there in the end. They selected Kyber. Many people are quite critical of Kyber. It's funny that we're not even at Kyber 512. We've almost like went to 768.
Yeah,
So
yeah,
almost like the first level doesn't exist anymore.
yeah.
And then there's worries that it doesn't scale quite as well if we wanted to go above the 1024. So do you think Frodo might get standardized sometime in the future?
I I do think so. I think the current status of Frodo is the ISO standard, the International Standards Organization, so different standardization
Mm.
body than NIST. They're kind of, I think, more European influenced and focused. And so, yeah, so Frodo I think it got knocked out in round three of the NIST competition. It didn't make it through to round four. But basically, the idea behind Frodo was, if we go back to that hand wavy explanation of learning with errors before, where we were talking about this public matrix A. By the way, in practice, not everyone in the world uses the same public matrix. When we go to turn it into a chem, then I just send you a seed
Yeah.
that's fresh for every time I do a chem. So I send you a seed that generates the matrix. The difference between Frodo and ML Chem is, in Frodo, the matrix is really a random
Mm.
matrix. There's no structure to it. ML Chem is a very different thing. It's still you could still parse ML Chem into a matrix vector. And there is still an equivalent matrix vector explanation of or description of ML Chem, but the matrix has been chosen in a very structured way that allows things to be a lot more efficient. So the matrix is basically kind of, every row of the matrix is a shift of the previous one, and I think they call it a negacyclic shift or something like that, where you're shifting the row, and but basically it's the equivalent is working in a polynomial ring modulo an ideal. And so this was the idea. I mean, Entru, which was from the 90s, was already doing something like this. I think they just used a plus one where they used a minus one where they should have used a plus one, and then otherwise it's kind of ring LWE. But then Lubashevsky, Regev, and Pikert and Regev, I think, were the ones who took LWE and gave the ring version, which is kind of the first step towards turning LWE into ML Chem. And so Frodo, so that was all done before the NIST competition started. That people realized that the ring, it looks like nobody knows whether adding this ring structure to the matrix introduces any catastrophic weaknesses or not. we believe it doesn't, and NIST and everyone that's going to implement the next standard is banking on the fact that it doesn't introduce any vulnerabilities. But the idea behind Frodo, which kind of came after some early work using the rings, was to say, okay, let's do a scheme that goes back to plain LWE, where there is no structure. So you lose a lot of efficiency. Bandwidth becomes a lot bigger. Public keys are worse, and so on. But you're kind of hedging against the structure that's introduced in the ring, or in the module LWE, which is what Kyber's based on. So I guess in that way, Frodo's like a more conservative lattice space scheme, which was the whole motivation behind doing it. In that paper, we were kind of saying, okay, what's the performance? In the original Frodo paper, it was like, what's the performance hit of reverting back to plain LWE versus ring LWE? And then it ended up being turned into a NIST submission, just in case NIST were going to be very conservative and pick the conservative option. And turns out they didn't. But then I think the German, the BSI, and maybe the Dutch and the French governments were all keen on Frodo and kind of endorsed it to ISO. And therefore, I think it's on track alongside, I believe, McLeese and Kyber. They're the three that I think ISO are going to look at or are on track to standardizing. And then time will tell if it gains traction in the market or not. NIST is sometimes viewed as the be-all and end-all of the standardization process, but oftentimes, as we've seen with like Curve 25519, for example, later down the track, they can see that it's being used, and for kind of interoperability and compatibility requirements, NIST end up rubber stamping it down the track. So that could happen too with Frodo if it gains traction through the ISO standard. But it's unclear whether it's going to be used by the masses.
Yeah, it's a typical NIST approach of a balanced scorecard. So performance is one of the key things. Even though the performance is going to improve all the time, when they're benchmarking, they'll give a score for performance. And obviously Frodo doesn't do as well. I think it's maybe about 30 times slower for key pair generation, which obviously is important in chem, but not important in encryption. If you think about it, McAleese is obviously not possible in key exchange type, but if you're long-term storage of a key or something like that, then it's perfectly acceptable. So I suppose it's that security, scalability versus the performance. And Kyber just basically won in virtually every area overall, and obviously it can fossilize. You saw that SHA-3 with Kecha kind of fossilized that, where we didn't need the number of rounds that were required for the hashing methods. And we now see Kangaroo 12 reducing number of rounds, but the standard is still back in the original one. So hopefully it will be more adaptable. And I see it in a lot of libraries. Frodo is implemented. And I think there's definitely use cases for it. Is it 640 is the starting point?
Yeah, that's the start. The starting 640 by 6, is the starting dimension. Yeah. And I think, to go back to your point about the metrics in these competitions and stuff like that, it is a very hard argument. When all of these scoreboards are being considered and people are, everyone's comparing all of their schemes to each other, and everyone's trying to get their scheme across the line to win these competitions to be standardized. When something's a factor 30 slower, and the reason you're giving is, there might be an unknown attack that we don't know of. That's kind of with the market being the way it is, people, the early implementers, the big companies like Google and stuff that were experimenting with these things, they're not going to take a factor 30 performance hit for something that, in all likelihood may or may not exist, when nobody knows, and it's a hypothetical kind of thing. So but then there's the argument that people in our field who have been around for a while say, no, it's always, no matter what, it's always better to take the conservative security option.
Yeah.
Yeah, so these trade-offs are it's always very interesting to see how it plays out.
Yeah. I thought Intro was the one that but just slightly slower and it obviously was more fundamental in its approach. And I was surprised that Kyber was selected over that one. But we'll see how that actually goes. And obviously we've got HQC coming along, which
Yeah.
performed pretty well before, and that's more a code base one. Is MacLeese ever going to get over the line too?
I think, well, yeah, I think for the same, I think kind of Frodo is to
Mm,
ML Frodo is
mm,
to Kyber as McLeese is to
mm.
HQC.
Yeah.
Because HQC is like the structured version of McLeese and Kyber's like the structured version of Frodo, or maybe yeah, Frodo's the unstructured version of Kyber. But yeah, so I think from the conservatives out there that have been around for a while and seen aggressive performance choices lead to catastrophic security failures might, be in favor of these more conservative, less performance schemes. I don't know if I think McLeese is going to be pushed through by ISO as well. So depends again. I think once things get standardized, once they're in the standard, then the market kind of does the rest of the work from there. And from from what I've seen, the market tends to just go with the most performant because the people making the decision of which cipher
Yeah.
suite to make the default, they want to
Yeah.
see performance. And so, yeah, these things, the more conservative ones kind of might sit in the background for a while. Or,
Yeah.
we could see a structured code-based system fall prey to an attack, or a structured ladder system fall prey to an attack, and then Frodo and McLeese are sitting there standardized and ready to go. That'd be good too.
Yeah. Yeah. I suppose it's all down to FIPS 140 and only certain industries really need that robustness. Other ones should be a
Yeah,
bit more dynamic, especially when it comes to hardware implementations and long-term security. Because a networked printer has got to be running for 10, 15 years and so on. So
right.
you can't just implement something today and be assured that in 15 years it will still be secure. So I think they'll be a lot more conservative when it comes to embedded devices and hardware as they are and more in a software type application. So the what's Geppetto? Hopefully I'm getting that right. Geppetto?
Yeah. Oh, Geppetto. Yeah. So that was Geppetto was, well, even though I'm a co-author on the paper,
Mm,
I'm the wrong person to ask what it is. I still don't
mm,
really understand what it is, to be honest. I know what it does at a high level, but
mm,
the way that I was involved in that project. So this was, I think it was 2014, 15.
mm,
We had a bunch of people at Microsoft Research that were working on verifiable computation, and they came to a colleague, Michael Narrig. He's the N in BN curves, um,
mm,
and
mm,
him and I were the kind of
mm,
pairing based cryptographers at Microsoft Research, and a team of people working on verifiable computation came and said, "We've got a very specific problem. We want to see if you can solve." And they kind of they said, "We want two pairing friendly curves that where the group order of one is the um, is the prime field of another. So that both curves have to be pairing friendly, but they're one's group order and the other's prime field have to coincide." And so we kind of came up with this Cox pinch construction, the thing that we just thought was very natural to do, but at the time it was like a very unnatural thing for us. I guess more curve purist. I didn't have I wasn't familiar with the literature on the zero knowledge proofs and what had been going on with the pairing based zero knowledge proofs and polynomial commitment schemes and so on. But it seemed like a very unnatural thing to be doing because if you know anything about elliptic curve cryptography, the fields and group orders are they're very different. They shouldn't really be. To make them coincide was a weird request. But anyway, we built this library where these two pairing-friendly curves were connected like that, and gave them this kind of building block that they did a whole bunch of other stuff on top of. And the other stuff at the time, I had no idea what they were doing. But now that I'm familiar with zero-knowledge proofs and what's been happening with the pairing-based zero-knowledge proofs, I now know what that paper was doing all these years later. So Geppetto it's a verifiable computation. So the idea is you want to outsource computation to the cloud because you're a tiny device that hasn't got much compute, and this is a big computational task. So you get the cloud to do it for you, but you also want a proof that they've done exactly what you asked them to do. And so that was kind of one of the driving motivations. And nowadays you see these in ZKVMs and so on. But the idea is to these pairing-based zero-knowledge proofs. They're giving you a very short proof that a very cumbersome computation was done correctly, and it should be very quickly for you to take that short proof and verify it. Turns out that the proof of the cumbersome computation is one thing, but the proof that the computation is correct is also, even orders of magnitude more cumbersome. It makes everything way, way worse. But again, that's the cloud's problem. It's not your tiny device's problem. So this kind of verifiable computation is that was one of the driving factors behind this kind of field that's totally evolved into something way more crazy nowadays. But Geppetto was, unbeknownst to me, my first taste of zero-knowledge proofs and pairing-based zero-knowledge proofs.
Excellent. And you published a paper on super singular isogenies. Can you outline how these work, and are we likely to see isogenies being deployed in the near future?
I really hope so one day. I wouldn't say in the near future. At one time in the not too distant past, I had that hope. My hope was that Psych was going to be as awesome as I thought it was, and was going to be standardized, and then one day would be the default level, the default way that key encapsulation was done, and then that scheme that SIDH and Psych was broken now in 2022. So I'll answer the second question first. I really hope that I think isogenies at the moment are playing the long game. So there's I think the pure isogeny problem, computing an isogeny between two, let's say, two random supersingular curves in the supersingular isogeny graph, computing that the walk between those two curves is exponentially hard and exponentially hard on a quantum. So classically exponentially hard and exponentially hard on a quantum computer as well. And that's kind of the fundamental problem that sits underneath isogeny-based cryptography. But to go back now and answer the first question, which is what are they doing? So yeah, we know that Shor's algorithm breaks the discrete log problem. So that was, we typically fix one elliptic curve that everybody on the planet uses, curved P256 or 25519. Everybody uses the same curve. It's kind of part of the public parameters. And we do discrete log-based cryptography, elliptic curve discrete log-based cryptography using a fixed curve. Because of Shor's algorithm, we can't expect to do that in a post-quantum world. So isogeny-based cryptography works in a very different way. It's not using one fixed curve anymore. It's an isogeny is a map between an elliptic curve and another elliptic curve. It's a homomorphism. It's a group homomorphism. So it takes all the points on this curve to points on this curve. And what we do in isogeny-based cryptography is we take a walk starting on a given curve. We take many isogenies away from that curve, and they all of these curves are connected in a beautiful thing called an expander graph. And we take many isogeny jumps away from that starting curve, and we end up somewhere else. And then the hard problem is if you forget about the jump, so that's like your secret scalar in discrete log-based land is that walk. if you forget about the secret scalar, or in this case, if you forget about that random walk and you just take those two nodes of this graph, which are elliptic curves, the fundamental hard problem is to find the walk between those two curves, or those two nodes in an expander graph. So I've got a hope or a belief or I don't know. I wouldn't bank on my intuition because I've been wrong in the past, but I've got a hope and a biased gut feeling that this problem will remain hard, because when you it feels like it should be hard. And so I'm hoping that schemes that future schemes can get closer and closer to just basing their security on they can maybe reduce their security to that problem. And in that case, I think isogenies in the very in the not near future, but maybe in the decades to come, will make a comeback after the I guess the first kind of popular isogeny based scheme psych was catastrophically broken a few years ago.
So NIST really wanted an alternative to the lattice approaches, and I think it wanted the isogeny approach to actually work, and it was just a bit unfortunate that Psych SIDH was cracked. What actually happened? Because it got through to round three, as I remember,
Yeah,
for it. And what
it,
happened with that?
I think it got through to round 4
Oh
in
yeah.
2022.
Hmm.
It was one of the alternates.
Hmm.
And at that point, I don't. At that point, I think NIST had said they were going to take 3 key exchange mechanism, key encapsulations, and 3 signatures, and so Kyber was already chosen.
Hmm.
And then of the alternates, I think 2 were code based.
HQC and
Um,
bike.
right, and then there was Psych as well, and maybe there was another ladder scheme. I might be,
McLeish.
or maybe there were 3 code. Oh, McLeish. There you
Yeah,
go. So
yeah.
3 code based and 1 isogeny.
Hmm.
And I was thinking, if they're going to take 3 and they're going to keep a diverse portfolio, then
Yeah.
we're home and hosed. Psych will be one of the 3, just from a diverse portfolio perspective, as you say. But then a month after that announcement was when the catastrophic break was announced, and I was actually either fortunate or unfortunate to be one of the first to know, because um, in my infinite wisdom a year before, I'd put up a bit of money as part of a Microsoft bug bounty challenge to say, if anyone can break these tiny toy examples of SIDH, the SIDH problem, then here's $50,000. So I convinced the bug bounty team at Microsoft that it was never going to happen, that their money was safe, and then a year later they were having to cough up. But so the two brainiacs, Kashrik and DeCrew, that found the break, and it's a gorgeous
Hmm.
it's a gorgeous break, and it's a beautiful bit of theory that they use to do it. Um, I got an email from them one Friday afternoon saying, "Oh, here's the secret key for your challenge. So we'll take the 50K. And by the way, I think it's polynomial time, this attack, and so it doesn't matter how big the parameters are going to be. You're toast." So that was one of my least favorite days as a researcher, was to see that. But no, once I saw the details of the attack and everything that was used, it was gorgeous, and I think I was heartbroken for a little while back then, because I wanted to see isogenies get standardized, just because I wanted to keep working on them forever, because I love elliptic curves. And so in my mind on that day, I was like, oh no, now, isogenies aren't going to be around in the post-quantum world. Lattices will forever be the one and only, and elliptic curves will die once everyone moves to post-quantum. But the really cool thing that's happened is that attack has now been used. The theory that was used in the attack has now been used constructively, which has happened a lot in cryptography, when something's used destructively, then later on, just like pairings were used destructively, then later on it was shown that they could be used constructively. And Valter Kastrik, one of the people who found the attack, he gave a talk at Eurocrypt, I think a year after the attack, or maybe 2 years after his invited talk, where he says, this attack looked bad for isogenies, but it's given birth to a whole new range of possible, improvements and better schemes and so on. So my dread that the field of isogenies was going to die with psych was soon shown to be, fortunately not true. Isogenies are alive and well.
Yeah, and obviously there's the additional signatures round two, and I think there is still an isogeny-based method that could be used for signatures. So although it might not be used for chem just now and for encryption, then obviously there's still, and I think there's a good chance it will, I think it's SQI sign
Yeah,
is the
ski
method.
sign they call it.
Ski
And yeah,
sign.
it's
Wow, that sounds
beautiful.
good.
It's
Yeah.
again beautiful, and again the biased kind of curve-based cryptographer in
Mm.
me
Yeah.
wants to see it
Yeah.
standardized, or
Yeah.
evolve into something that's used in practice. And time will tell. I hope a lot of people are trying to break it, and I hope over the course of maybe years or decades that won't happen. Or if it does, that a better scheme that's based on a more kind of pure instance of the isogeny problem
Mm.
will be proposed. But ski science being improved all the time, the performance, the security analysis, and so I'm excited for ski sign. I'm kind of sitting cheering from the sidelines.
Yeah. E- Excellent. And so, how does pairing-based cryptography, we talked about pairing-based cryptography earlier. Do you have a simple explanation of how pairing-based cryptography actually works and what's the core applications these days?
Yeah, a simple explanation. A simple explanation. I don't. So maybe if we're talking about, if we go back to the discrete log setting,
Mhm.
um, where you've got, g to the a modulo p, let's say, is an instance of the integer discrete log, and so you can take different you can take different instances of that discrete log. So g to the a mod p, g to the b mod p, and you could multiply those two instances together and get the kind of additive sum of their exponents, right? So you can take g to the a mod p and g to the b mod p, multiply them together, and you get g to the a plus b mod p. And so you kind of get this additive homomorphism in the exponents. What pairings allow you to do to some extent is, and additive homomorphism, there's a lot of cool things you can do with that. You can build voting schemes and so on. But what you would want for more kind of functionality is perhaps to be able to multiply in the exponents as well. Well, if you could combine g to the a and g to the b and get g to the ab in an easy way, then the Diffie-Hellman problem would be easy. So we don't necessarily want that. But for functionality, we might want to be able to perform multiplications in the exponent, and a pairing allows you to do that. So a pairing, now we're not talking about g to the a and g to the b anymore. We're talking about points on elliptic curves, because for the magic of a pairing to work, you have to, fortunately, for those of us that loves elliptic curves, the only way that we know how to instantiate these secure bilinear pairings in practice is using curves. And so you can take two elements and compute a pairing, and then in the target group you get that kind of multiplicative homomorphism of these exponents. And there's a whole range of applications that you can build out of this property, this bilinearity property. Now, in the early days, a lot of the applications that were kind of used that gave birth to the field were like identity-based encryption and attribute-based encryption and things like that. Predicate-based encryption. The list goes on, and there's, if not hundreds and thousands of papers that have been written on all these pairing-based constructions. When I got into the field of pairing-based cryptography, I was kind of working on the computational stuff. This was in my PhD, 2008, 9, 10, 11, 12. when I came out of my PhD, I was very, very laser focused on pairings because it's the only thing I'd been reading about for years. And I came and started working at Microsoft and kind of saw more of what was going on in cryptographic practice. And was kind of disappointed to see that they weren't actually being used anywhere, that identity-based cryptography was not, it wasn't as neat as I thought. All the papers I'd been reading were saying it solves all the world's problems. And, it turns out that PKI was doing just fine without pairings. And so I was a little disappointed to see none of these applications were actually needed. There was other ways to do them or other things that had gained more traction. So I kind of left that field and worked on other things for a while, and then these Gross style pairing based zero knowledge proofs. Since before Gross, so KZG polynomial commitment scheme from 2010, there was zero knowledge schemes coming out before that kind of gave birth to this lineage of pairing based zero knowledge proofs. And nowadays, pairings are used all over the place in the zero knowledge world. So the popularity of cryptocurrencies, Bitcoin, Ethereum, and so on, the blockchain, it has kind of resuscitated the field of pairing based cryptography from my perspective. And now they're used all over the place because of these very short, succinct zero knowledge proofs. I'm not sure if I gave a good explanation onto how pairings work, but it's kind of hard without getting into the weeds a little bit.
It's very difficult, yeah. So something like g to the power of a paired with g to the power of b, like if we're thinking of logarithms, it can become g to the power of ab paired with g
Yeah, yeah,
is obviously one way of looking at it. And I like the example where you've got a quadratic equation, x squared plus 2x minus 3 equals 0. I can provide you with a zero knowledge proof using the methods you outlined that I know the answer X is one of the proofs. So they're quite wonderful, but I think there is so many uh, 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 difficulties and they're doing lots of different things with polynomials and so on that I think sometimes it hides the magic that goes on
yeah,
underneath.
yeah. That quadratic example you talk about is it's
Mm,
beautiful to see it.
mm,
But then what they've got to do with these snarks and Starks and all these really complicated protocols is they've got to kind of parse these
yeah,
general proof statements into this quadratic polynomial framework somewhere at the bottom so that they can use the magic of pairings down below.
that's right.
And this infrastructure that they build on top of this little magic quadratic proof that you talk about is becomes very complicated and very cumbersome. But fortunately, in that field, all of that cumbersome work is in practice, it's something that you might, the prover has that computation. Let's say there's scenarios where the prover can afford to take seconds or minutes if they have to,
Yeah,
and the verifier gets the very small proof and they get to
good.
verify just using a couple of pairings, which is really, really nice.
That's right. In blockchain applications, it can take minutes to create the zero knowledge proof, but obviously the actual verifier it takes much less. So
Yeah.
they're beautiful in their scope. So what's a hyperelliptic curve and what's their applications?
Yeah, hyperelliptic curves is yeah. So hyperelliptic curves are the generalization of elliptic curves.
Mm,
So if we go back to something we were chatting about at the start with, degree one curve is a line.
mm,
Degree one in x and y. Degree two in x and y is a conic like a parabola or a hyperbola,
mm,
something like that. Degree three is an elliptic curve,
mm.
which is genus one. So there's a measure of geometric complexity called the genus. And elliptic degree one and two are genus zero. So geometrically, they're kind of they don't give us anything in terms of hard discrete logs in cryptography, which is why we love elliptic curves in cryptography. But then, as soon as you go to degree three and above, you can get degree once you get to degree five and six, that's a genus two hyperelliptic curve. Degree seven and eight is a genus three hyperelliptic curve. So So they're kind of the higher dimensional generalization of elliptic curves. Now, the difference between I'll stick to genus 2 because that's the kind of next easiest version of a hyperelliptic curve to describe. Genus 1 is the elliptic curve where your group elements, if we're talking about the algebraic, an algebraic group element, the geometric the geometric equivalent of that is a point on the curve. Essentially, there's a trivial map between the kind of abstract, the algebraic group element and the geometric point on the curve. So you can basically take group elements as points on the curve. When you go up in degree, you no longer get a group law if you're just talking about the points on the curves themselves. So you have to you have to know a little bit more about algebraic geometry, but you're essentially in genus 2, your group elements come as pairs of points on the curve. Okay, so an algebraic group element corresponds to a pair of points on the curve with some other details I'm sweeping under the rug. And then as you go up the genus, roughly speaking, the number of one group element corresponds to more points on the curve as you go up the genus. The whole rationale behind the whole interest into hyperelliptic curves was, I guess, kind of following the thread of why elliptic curves would be superior to finite fields. It was, no index calculus means that we could use a lot smaller parameters and a lot smaller fields to get the same security. With hyperelliptic curves, because of that fact, in genus 2, for example, your group elements are pairs of points. Basically, the size of your group, roughly speaking, for an elliptic curve over a prime field, the size of your group is roughly the size of that prime field. For a genus 2 curve over a prime field, the size of your group is roughly p squared. Okay, so put another way, if your genus 1 curve has to be defined over a 256-bit field, you can get the same size group with a genus 2 curve over a 128-bit field. So the whole idea was, and Koblitz was the one who, a few years after he proposed elliptic curve cryptography, said, well, we could do hyperelliptic curve as well. The whole idea was, well, maybe we can keep going down smaller in the field, going down the field and shrinking the size of the field. The trade-off's a little different, though, because as you go up in the genus, the complexity of the arithmetic grows as well. And so, the operations you're doing in these half-size fields are a lot more difficult than the genus 1 operations were, the elliptic curve operations were. But the idea was that maybe more operations in a field of half the size will be faster than fewer operations in a field of twice the size. So that was kind of the efficiency, the performance motivation. And then years later, it came out that all genuses were on the table initially, as far as I can tell. So arbitrary genus was interesting, but then very soon people realized that you could do in genus 3 and above, there was a way to do meaningful index calculus. So there was a way to build factor bases. There was like an analog of the finite field index calculus that you could do on curves of genus 3 and above. That made index calculus better than Pollard row. And so basically we're left nowadays with genus 1 and genus 2 in the discrete log setting are the only ones that are immune to index calculus as far as we know. There's no, in genus 2 you could still try index calculus, it's just not better than Pollard row. So they're the only ones where generic attacks are still the best. So genus 1 and genus 2 are still alive, or still as good as they ever were in discrete log-based cryptography. In isogeny-based cryptography, all genuses are still on the table, as far as I know. And I think the trade-offs are even more favorable in isogeny-based cryptography. As you go up the genus, you get more rapid mixing and richer expander graphs, very roughly speaking. But I think also at this stage, we know so very little about isogeny graphs beyond genus 1 that it's very early days for higher genus hyperelliptic curves and so on in isogeny land.
And I think you published a paper on how to select new elliptic curves. And I know that Daniel J. Bernstein has a website that actually defines safe curves and not safe curves. And there's a lot of debate about that classification between safe and not safe. What was your
Yep.
main recommendations for picking a new elliptic curve?
Yeah, well, we when we wrote that paper, I think we were still not ready to say goodbye to prime order curves. And that was kind of, I think we were the only, or like, yeah, I guess the only people actively participating in that, selecting the new standard of elliptic curves that were still like, oh, hang on, let's not, you know, prime order curves, let's keep it under consideration. So in that paper, when we were talking about selecting elliptic curves, I think we had three different security levels, and at each security level, we had the kind of fast Edwards or Montgomery curve. They're kind of equivalent um, over a given field, and then we had a prime order Weierstrass curve over the same field. And basically, we wanted to look at the if we're gonna introduce cofactors, you know, so curve 25519 and Edwards curves, they all necessarily you can't construct them over the prime field unless they have a composite number of points. And all elliptic curve cryptography before then was always of the kind of went under the assumption that the best thing to do is to have a prime order number of points, because then basically once you get given a rational point, you check that the coordinates satisfy the curve equation, and you're guaranteed that that curve has prime order.
Yeah,
Whereas on a composite order curve, you might have to multiply it by the cofactor or do something else to make sure that you've got a secure discrete log
just
and no small
like curve
subgroup attacks.
25519 has this factor of 8 in there.
Right, the factor of 8 that Dan gets around that by forcing his secret keys to have a factor of 8 at the end so that it
Clamping.
clears that. Yeah, so he's got a clever way of getting around that, but we kind of wanted to also keep prime order Weierstrass curves on the table, and basically to give like curves that were like the NIST curves, I guess, but that were deterministically chosen in a different way than the NIST curves, but that were prime order Weierstrass curves, which everyone had been implementing for the longest time. And I think we got crushed on the mailing list for the prime order suggestion because of the reasons that people like the composite order approach, which is there's some implementation security. When you implement a scalar multiplication on a prime order curve, there can be, in an implementation, there can be branching you have to do to worry about whether you're running into the inverse of a point, or then you might have to use different formula. And if you use the different formula, that might take a different that different execution path will take a different amount of time, and that might leak information about your secret and so on. So in that selecting elliptic curves paper, we wanted to have a look at the performance trade-off essentially between Edwards and Weierstrass, and the performance that you lose to going through a prime order curve, which I think was around 20%. It wasn't too bad. I think the reason prime order curves got slammed was based on all of those other implementation faults that could arise, which is fair. But then not long after that paper, I had a student that I worked with where we said, okay, let's go and try to find a set. Let's try to go and find complete addition formulas for prime order curves, because it was kind of these composite order curves. They have a single addition formula that works for all input points, which is what makes Edwards curves very attractive. That you can have one formula that will always work. And so myself and this student, we were looking at trying to find the equivalent for prime order short Weierstrass curves, which wasn't known at the time. And it turned out to fall out of an older paper that we looked at that kind of already had written it down. We just basically, we basically took that paper and wrote it down and presented it to the practical cryptography field and said, actually, you can do complete addition algorithms with prime order curves too, and it's not too bad at all. So I'm still a fan of prime order curves, and I still think they can be implemented, as securely as composite order curves.
Exactly. And do you think that NIST P256, which is the SEPT 256R1, and the Bitcoin curve sept 256K1 are safe or not?
Yeah. Okay. Right. Yeah. So, well, um, it'll always depend on the implementation. So no curve is not even curve 25519 is
Mm.
um, safe by default. It has to be implemented in a safe way. I think the high level idea that I guess Dan and Tanya and those pioneering, they have this Safe Curves website where they were classifying safe and unsafe curves. Their idea was trying to minimize the pitfalls that implementers can run into. And so that's when they kind of went and deemed a lot of the prime order curves as unsafe because of these potential implementation pitfalls that implementers might, implementers might forget to check that points are on the curve when they come in. And his implementation, you don't need to worry about that. All very valid points, but I would push back and say no, prime order curves can definitely be safe, just like composite order curves. They've got complete formulas. And in fact, there's instances where the composite order curves could be unsafe because of small subgroup attacks. If you forget to do the cofactor clearing, then you might run into trouble when you don't have to do that on a prime order curve. So for me, it's not as cut and dry as safe and unsafe, and I think it depends on all of the context of the implementation.
Yeah,
And so yeah, I do think that those two curves are safe. And I mean,
yeah,
if the Bitcoin curve, people that was also deemed unsafe, I think, because it's got an endomorphism, a low
yeah,
degree endomorphism.
yeah,
But that's all speculation.
yeah,
Yeah. There's no evidence that, with the exception of a tiny, small, like very tiny, concrete uh, constant factor, like 1 or 1.5 or 2, a factor 2 speed up to Pollard Row. There is no security concern that we know of curves with an endomorphism. Um, and if there was, that Bitcoin curve is like the most lucrative target. So I think if there was a problem with the Bitcoin curve, we would have probably seen some Satoshi coins moving around already, if someone knew how to exploit that problem. And yeah, until we see those coins move around, then there's probably no problem with endomorphisms, or a quantum computer hasn't been built, unbeknownst to
yeah.
the community.
And we should say that the prime number that's used for the curve is different from the the prime order. So
Right.
prime order means that you have a prime number which is equal to the number of points. So the prime that you're using in the elliptic curve doesn't have to be prime necessarily, but it ends up, and I think curve 25519 can be turned into a prime order. There are certain methods around to do that. So
Right.
that's the big difference in that P will be bigger than the order
Right.
n, but and I think that's what you're saying is that the order becomes a prime number overall.
Yeah. Well, I mean, exactly as you say, that there has been a lot of work done to kind of to basically handle the cofactor of that curve. So these Ristretto algorithms, or the Ristretto framework, that
Yeah,
basically says we want to make it impossible for implementers to fall into these small subgroup attacks, maybe, or to leak information about the key in case they forget to clear the cofactor. So that framework kind of builds a prime order cryptographic group, or exposes an API that allows you to access it as if it's a prime order group, even though it's technically not underneath. It's a composite order elliptic curve.
yeah, yeah. So composite order means there's a multiplication of two prime numbers
Yeah, or more.
underneath,
Yeah,
or
yeah,
more. That's right. So for eight, you've got two times two
yeah,
times another
exactly.
prime. So that's where the curve 25519 has this sub-order of the eight. And I think the way that Daniel J. Bernstein did it was to mask off the bottom four bits, which can be quite strange when you're trying to do some computations about, well, that doesn't quite work. And you've got to
Yeah.
remember the last four bits. And I think there's an attack called the octal attack that could be done on like a cryptocurrency that overcomes.
And I'm glad you brought that up because when that because all the while when these discussions were happening about prime order
Mm,
versus composite order, and prime order curves got a really bad rap for being insecure because of these implementation pitfalls. It's interesting now, and I mean, don't quote me on this, but I still don't know of a real world attack that has
mm,
exploited the prime order the hypothetical pitfalls. But I do know of that one that you spoke of that did exploit the composite order attack in their case. So I
mm.
mean, there's a little bit of irony there that that the composite order curves were brought in, were touted as being safe to implement, much safer to implement, whereas that wouldn't have happened in a prime order case. So
Mm.
until there's a devastating attack on a prime order implementation that uses that branching, they're kind of speculative attacks anyway. But it is the principles that they talk about trying to minimize the errors for implementers that might just read a spec and implement and screw something up. That is
Yeah,
obviously good practice, and it is a good motivation. But I still
yeah,
I still am a fan of prime order curves, even from an elegance
yeah,
perspective. I think there's something really nice.
yeah. Everywhere I look, it's Ed 25519 and X 25519. They're just the curve of choice at the current time.
Yeah,
Performance is great. Obviously, the key sizes are much smaller, and I think the security is much better. I think the problem
yeah,
with P256 and SEP 256 key one is that the original designer didn't actually show how the original seed or hasn't revealed the original seed value. Hopefully,
yeah,
they forgot it very quickly. It was someone, I think, from the NSA, an
yeah. It was
ex-employee.
Jerry Salinas, I think.
That's right. And there's a worry about, and I think it was Mike Scott. I might be wrong, but it was Mike Scott who communicated with him,
Yeah,
and
you,
he reckoned, yeah.
you're absolutely right. It was, I think, Mike Scott was the first one to point it out when the NIST curves um, were first, I guess, published in, I think it was '99.
Mm-hmm.
Um, it might have been that year or like the year after that. Mike Scott had a blog post somewhere saying,
That's
um,
right.
yeah. So basically, the curve constant B is the output of hashing. You can show that B is derived from the output of a hash function on its seed. So they said, here's the seed, B is the output of the hash of that seed, or B is some function of the output of the hash of that seed. So we couldn't have possibly controlled B, so we had nothing up our sleeve. And he made the point, well, you could have just tried a million different seeds until you found one that hit a weak curve that you know of. So that was the argument there, which is, it was very quick of him to see that. Um, and so yeah, the argument there being that's what that was another reason for people to be speculating that maybe the NIST curves there is a weakness, so we need to replace them with something better. Um,
Yeah. And
yeah,
we obviously get the track record of the NSA trying to influence the random uh, generate
dual
elliptic
EC.
curve random generator. I think it was Microsoft that actually found that
Yeah,
one too. So it wasn't a great track record that NIST had
no,
been
that so
trying
that
to
that was another
influence
thing that
things.
once the Snowden documents came out, I think that was a speculation that Ferguson and Schumo made at
Ferguson,
the
yeah. Yeah.
2007 rump session at
Mhm.
crypto. They said
Yeah.
they could have backdoored it. This is how they would have done it. This is how easy it would be. Because they just had to publish. They had to publish
Mm.
2 points, and if you know the discrete log between the 2 points, then you can break it.
Yeah.
And then I think the Snowden leaks confirmed that they actually had been up to no good. So that was yet another reason to kind of say, well, if they're up to no good, they could have totally backdoored the NIST curves.
Yeah.
But I think in trying to prove his innocence, this is folklore now, but I think Jerry Salinas from NSA has tried to go back and recompute the curve to find out what the seed was, and I think it's something like the initial starting seed was like the hash of the string. Jerry Salinas deserves a pay rise or should have a
Yeah.
rate. It's something like that.
Yeah. Yeah.
But yeah, anyway, no one's been able to reconstruct the method to
No.
NISCAs, which makes the speculation all the more fun. But
Yeah.
I don't know. I tend to think that they're fine.
Yeah. I
Um,
think that Daniel J. Bernstein has crawled through the minutes of the meetings that NIST had around the PQC standards to look at what influence the NSA actually had in
yeah.
influencing. And so there's still a little bit um, of a question mark around the influences, but obviously NIST would go to the NSA and ask for some cryptographic knowledge from them. But obviously there's a worry that they might have a method that would break something. But as far as I could tell, it was typically research papers from academia that were publishing work, and it's been well peer reviewed over the time. So fingers crossed there isn't any backdoor in there. I mean that brings
Yeah.
us back
It's,
to crypto wars again, which in
yeah. Yeah.
Australia is quite tough. I know that Australia has a deadline of 2030. Am I wrong?
Yes. No, no,
For
you're right.
migration towards to get rid of
Yeah.
classical public key and the most aggressive country in the world. I don't understand why they've done that. Is that a
Yeah.
lack of
It's
knowledge, do you think?
um I'm gonna be patriotic and say no. No, no. I've read the document, the kind of website as they keep, modifying and updating over the years. The last time I read it, the wording was sort of unclear. It was like in 2030 we're going to stop supporting the classical stuff, which to me I don't know what
Okay.
that means specifically, but by 2035 we're going to prohibit it, which to me says okay, that's the hard deadline where
All right.
it's going to
Missed.
be
Yeah.
yeah. And I just saw someone from ASD give a talk that so they're also I think um they're also going for 1024 MLChem 1024 as the only thing they
Wow.
recommend, which I thought was
Wow.
interesting.
That's
I,
crazy.
I'm pretty sure it's not 768. I'm pretty sure it's
Yeah.
1024. And my thought was like, immediately you go to the fun hypothetical scenario of what do they know that we don't, or something like
Yeah.
that. But
All
then when he
right.
gave the talk, he said, no, actually, we're just doing it to like take the headache out of maintaining all of
Yeah.
this stuff. We're just going to go for the top one. And I think I think in the signatures the same thing, which I thought that was interesting. But also, yeah, that is more aggressive than what most countries have said. Um, I tend to like. I'm a big fan of the hybrid. I don't think anyone should throw the classical baby out with the bathwater yet. Especially having been on the wrong side of a devastating polynomial time classical attack on a post quantum scheme. I think the it's got to be hybrid, for a while at least. Um, Even one point I saw raised the other day that I thought was very interesting. I hadn't thought of yet. We think of the hybrid, ECDLP being alongside MLChem, and the rationale being, well, at least if there's a unforeseen classical attack on MLChem, then we've got the long-standing classical security of the ECC. A point that was made the other day in a talk, I think it was deliberate, it could have been accidental, but something that kind of tweaked when I was watching Jonathan Katz give a talk from Google, talked about the implementation security as being another reason for the hybrid. And so we've got a 20, 30 years now of implementation pitfalls that we can do a lot. We know how to do timing and power analysis, protected implementations of elliptic curves, and there could be a lot of implementation attacks on MLChem that we haven't seen yet, in the wild. So it might be a good idea to just do the hybrid from that standpoint. Because at least if someone does a timing, a sophisticated side channel attack on the hybrid, they might be able to do something we haven't foreseen for ML Chem, but maybe not for the ECC. I thought that was another interesting reason to go for the hybrid initially until we're sure we're getting the ML Chem implementation right and MLDSA.
Yeah. Excellent. Well, this is my penultimate question. And why select academia over industry? Obviously, the salaries are probably not as high, and in academia, but the holidays can be better, especially if you have a young family and so on. So, what
Yeah,
choice, apart from moving from the US to back to your home country, why make that jump between? And many academics are jumping the other way just now. I see many
yeah,
cryptographers moving into industry because
yeah,
of that reason that they can work at the state of the art. They have teams, they get better paid, and so on.
yeah.
Why have you decided at this part of your career to make that jump?
Yeah, it's and thanks for the question. It's yeah, a fun one to finish on. I loved my time at Microsoft, and it was invaluable for me for many reasons. And but I think I've always been an academic at heart, like a pure academic at heart. One of the things that I wasn't able to do in the industry job, I mean, having now done a year in academia, I know how hard it is. It's to me, it's a lot harder um, to juggle all of the things, the teaching, the grant writing, the supervision, and all that sort of stuff, and somehow manage a research agenda is a difficult thing. I think for me, one thing that I'm really looking forward to doing is having a longer term relationship with students. And so at Microsoft, we were super. I was really lucky to kind of have my pick of the litter for interns every year, and we'd get PhD students from all around the world that we could have for a 3 month summer internship. They'd come, we'd do a 3 month project and maybe write a paper together, but then they'd go back to their PhD supervisor and never to be seen again in some cases. Um, and one thing that kind of prevented was really like long term ambitious collaborations with students, that you would get in a PhD student. Um, and I think so that's something I've always kind of missed. I did have a few kind of adopted co-supervision of PhD students, which I really enjoyed. Meeting every week for many years, and that's another thing that's already I'm finding very rewarding here. I've always kind of wanted to build my own group of students and postdocs and team of researchers as well. And I think the thing that's attractive in academia is the ability to do that. And I think it's kind of it's another environment where you have the freedom to you have the freedom to do as well, to go as far as you're capable of, to do as well as you're capable of. And I think I've got ambitions to build a big team of cryptographers here. Not that wasn't possible, at Microsoft with that sort of money, but it's just different. It's different to have those long term relationships with up and comers, and to be in a position where you can supervise a PhD and then bring in postdocs for the long term. That's something that I've been excited about, and I don't think I was delusional about that, because I'm already really enjoying that aspect of kind of having that longer relationship with students. And the novelty of teaching hasn't worn off on me yet either. I think some people become a bit jaded after 20 years of teaching the same thing, but I'm kind of fresh faced in that regard too, and I'm really enjoying the teaching as well. So yeah,
And
I'm very happy so far, but yeah, time will tell if I go crawling back to industry with my tail between my legs.
yeah, I mean, it can be an opportunity to find research talent early on. Obviously, at Microsoft, you're seeing it a bit later, but being in a university, you can actually pick off some really great researchers who could make amazing PhD students, get them set up with projects and so on. And certainly, if you can teach well, then people will be attracted to your area and see the magic of it. So my final question, and probably I don't know if you've got an answer to this, but if you could change one thing about your career, what would it have been?
Oof. Oh, that's a tough one. If I could change one thing about my career, hmm, I mean, I've been super lucky with how it's all panned out. I was lucky to be hired at Microsoft and um to have that time there. I think my timing in coming home and getting back into academia's been very fortunate, having just started a young family. And I think it's, as you said, it's given me the flexibility to, to be present at home and to be at work as well. Uh, the things I can think of is probably more very, very like technical and
Yeah,
not more kind of high
technical's
level
fine.
philosophical thing. Yeah, I think
Get into early
I
elliptic curves
yeah, I think
earlier. Yeah,
maybe or getting into lattices
yeah.
earlier. Maybe like
Mm,
I've definitely I'm definitely very biased
mm,
towards curves, and
yeah.
I after we kind of proposed new elliptic curves and were beaten out in that standardization thing and whatever. I temporarily pivoted to lattices. I was trying to like look into lattices and stuff, and I felt very, very left behind. And it was like almost, it felt impossible to catch up to the people who knew that lattices are very easy to describe from a like constructive sense, the shortest vector problem or LWE. But those who really know all the subtleties seemed like they were orders of magnitude ahead, and there was so much catching up to do that it would have been 5 years without publishing anything um, before I could catch up to those that were, the leaders in the isogeny space, in the lattice space. And so I kind of got dejected and came back to curves. And I think when I started my PhD, I was starting to work on pairing computations kind of when it was drying up. And so maybe starting on lattices in 2008, 2009, in hindsight, would have set me on a different path to become a lattice person. But maybe I'm only saying that because ML Chem won and isogenies got beaten out. So no, I don't think I don't have any regrets from a like career decision standpoint. But maybe some technical things. I think quantum algorithms too is another one I'm getting into now, but I feel like a student. Starting from day one, I feel very yeah. So I kind of, these are things that I wish I'd been learning earlier, but it's only through the magic of hindsight that I now know that I wish that. So I don't really have too many big regrets in the career, but well, actually, one that I can think of might be that I wrote a white paper about psych before it got in the year before it got broken. I wrote one paper where I thought in the previous curve standardization discussion, I wasn't vocal enough about pushing for our elliptic curves, and so I thought, okay, now's time to, we're getting to the pointy end of the NIST competition. Now's time to be really pushy about how good psych is, and so I wrote a white paper on my own during my paternity leave about how psych was unbreakable and it was untouchable and it was the best thing since sliced bread. And then yeah, turned out turned out to eat my words a year later. So no, but I still don't regret that. I stand by at least one of the things I said in that paper, which was that one of the beauties of psych is that the best algorithms for breaking it, like you get no improvement from a quantum computer, which was true at the time. Basically, the complexity of the best quantum attacks was even worse than the best classical attack. And that I still stand by that. It turns out to be
Yeah,
true even now that the best
yeah,
quantum attack still doesn't compete with the best classical attack. So I at least stand by that sentiment. But
it's,
otherwise, it was yeah, I was getting a bit
yeah,
ahead of myself
yeah.
to be so bullish about psych.
It's all part of research. I remember Ralph Merkel and Len Edelman had created a knapsack public key crypto method, and I think it was Audie Shamir and Len Edelman that actually broke it live at a rump session of one of the crypto conferences. So
Yeah,
research is all about that. I create something, you break it, we fix it, and we evolve our
yeah,
knowledge through that. So thank you
yeah.
so much for giving your time. It's lovely to have someone who has a shared love of elliptic curves. I certainly have, and I'd love to see them evolve into the future. So thank you so much. It's been 2 hours of your precious time, but hopefully you've given our listeners the opportunity to see the beauty behind all of these complex maths. So thank you.
Thanks very much for your time too, Bill, and And thanks for everything you're doing with this podcast and with, giving us all a platform. And yeah, I really appreciate your time as well. Thanks for having me.
Thank you.